Test, test. Oh, I hear my. Yep, I can hear you now. Okay. So you want to go over
Yeah,
what does
that's
the
right.
code do? Okay,
Let me. How about you see my screen first? Let me show you
okay,
my
sure.
share screen, entire screen, go live. Oh, this is yours. So far, let me go over. Let me think. Tell me if you get any advice.
Okay.
And here, I just changed some to capital. And here, introduction.
Oh, that one's new, isn't it? Previous slide.
Which one? This one?
That one's new, right?
Yeah, this one's new.
Okay. Yeah, that'll be good.
Object. This one's new.
Yeah, that one seems important. One thing I would try to figure out how to configure is the last bullet point is getting very low.
Uh,
Oh wait, it's online. Never mind. You don't have to worry. Okay.
you mean the Elon
Yeah.
Musk?
Yeah, the Elon Musk one.
Okay, I would delete it.
If it's on Zoom, it should be fine. I was thinking if it's in person, some people might not be able to see it from the back of the room, but
Okay,
online is okay.
okay. And Waymo.
Okay. Line reader, camera navigation, save. Yeah, that's good.
And Q car.
You think that people in the defense will know what LiDAR is?
Cause I would not use, cause our project didn't use it,
Yeah, we didn't
but
use
I
it.
just put it in the future discussion, a future plan. Say,
Okay.
ongoing project will be done for the object detection in the future.
hmm Okay, yeah, that's a good
Yeah,
idea.
this one, the same. Yeah, manual control, the same. And demo here, the same. Here is the same. Mostly I've done for the length detection part, but
hmm
I just moved the CNN to the back in the end of the length detection process,
Okay.
and I just do the half transform, and I didn't do
hmm
the extrapolation of the lane line segment and the draw left right lane line. So I just put it in one slide for the half transfer for detect the line.
Yeah, that's
I
fine.
haven't modified for this slide yet.
Okay.
So here, but I put it wrong because we use the real sense one, but this one is CSI. So I just using this one to do the example for each of the process.
Yeah,
Here,
that's
convert,
fine for now. Uh-huh.
and for Gaussian filter.
Oh, you did it on each. Oh,
Yeah,
okay,
each
yeah, that
process.
that that helps. Yeah, that helps a lot.
But the issue is that for the region of interest, it's kind of weird because I define for whole the x 0 to 800 something, 880, and to middle of the point is 400 to 400 and 200 for x and
Uh-huh.
y.
Yep,
And the result is kind of weird. If you see this is region of interest, and
that
here
makes sense to me.
there's a lot of noise, and I cannot detect the right part.
Uh, what does the canny edge look like right now? Like the one right before Huff?
Yeah, I can detect here, but I don't know why. Because the triangle part.
what could be the reason? Huh.
Or do I need to move the right point to upper to detect more wide angle, a triangle?
Hmm. That might worsen your results. I mean, you could try it, like raising the triangle height, but I think it will worsen it because it's detecting that long line on the right-hand
Yeah.
side
Also the table, right?
and part of the table. Yeah.
Okay.
So that like tiny little line at the very edge of the image, I don't think it's detecting because it thinks the bigger line is the real
So
length.
when I doing this example, I'm thinking that this might be the issue for our turning part because there's a lot of noise when he detect the line.
Hmm.
So sometimes I just define it as the straight line.
Yeah,
Yeah, because the
that could
right
be
side
something
we
to talk
cannot
about.
define for the region.
Hmm.
Yeah.
Did you try another thing we could try
Mm-hmm.
is flipping the image. So like instead of looking at a right turn, look at a left turn and then see how the Huff transformation is affected by that. I don't think it will play a big effect, but that could be one reason.
Okay. And next here, I haven't finished CNN part. I
Okay.
just put one slide for this one. And then following is the one. I just put the demo first, and I haven't because I want to listen yours to put in my slide. And
Oh, okay.
and demo future goal I just put here.
Python on screen.
I'm not sure the because I'm not sure we have time to transfer the Python to raw.
No.
So I just put it first.
Yeah,
Yeah,
yeah, these are the objectives, yeah.
yeah,
Do we
and
need to explain no, that's fine. We don't think. I was gonna say should we explain why transfer from Python to ROS, but that's okay.
I will explain for like few
Okay. Ting Ting Chen will definitely
because
know
I have some
because
notes on here. Here you can just look it.
okay. Okay, I see.
Yeah,
And
I haven't read the conclusion yet. That's it. That's it.
wait, what's it what would you write about in the conclusion? Like final
Just wrap
response?
up.
Wrap up, okay.
Yeah. Then you want to show your screen?
Sure, I can share.
Stop stream. Okay.
I'll share my whole screen so I can switch between the code
Mm-hmm.
and presentation. Bring up code 2. Is this one it? Yeah, this one's it. Why is it not? Come on, give me the syntax. There we go. Oh. Okay, let's go over to presentation. Oh, I guess we can look at the code first.
Mm-hmm.
Um, there's 3 main steps that we're performing once we have Fong's, let's call that the lane,
Mm-hmm.
thresholding, warping, and some type of histogram calculation.
Mm-hmm.
This is where we determine our actual curvature, our actual point of interest. So we'll look into what these 3 methods are doing. So as mentioned, for calculating steering, 3 different operations that we have to do. And we start off with thresholding first.
Mm-hmm.
And that's the idea of you have some pixel value, um, which should range from 0 to 255. In our case, it's 0 to 255 cubed
Mm-hmm.
because there's 3 different values, or I guess 0 to 255 but averaged. And a singular threshold is saying if that pixel value is above a certain value, so maybe 170, then we can consider this pixel to have meaningful data. I need to change that, but yeah, meaningful data. And you sometimes don't want that, uh, like everything just above, because sometimes too high might be extraneous data. In our case, like the chairs and the computers, that might produce pixels which don't have meaningful data. So what we really want is a range. And that's what the double thresholding is doing. You put an upper bound and a lower bound, and all the pixels in between you can consider as useful information. So like pixel intensity from 70 to pixel intensity 155. There is another process which I don't think OpenCV implements, but should be implemented, which is called hysteresis. Hysteresis, I don't know how to say it. And it's the idea that if you have a region which satisfies both the upper and lower bounds, and it's adjacent to another region which is not in the upper and lower bounds, but might be very near to one of those bounds, then you can also include that data. So adjacent pixels which are touching a region that is both in the lower and upper bounds can also be considered meaningful data. So what we're doing with thresholding is removing pixels from the image that we don't think are useful.
Okay.
So that's step one. Step two is warping. Once we've removed the unnecessary pixels, we want to reshape the image to mainly focus on the road. So in our case, we want to create from a road into a bird's eye view image. So basically, the end goal is just make the road the image
So it's
instead
make
of
the
all the
rectangle
background
to
information.
the square.
Yeah, make this trapezoid into a square.
Okay.
And this is just linear algebra. There's a transformation matrix that you can use on the pixels or on the image to warp the image to create only the pixeled regions. That's this. And then these are just informations about it. If you don't remember a little bit about linear algebra, but this is Googleable. Perspective transformation is all you have to Google.
Okay.
Okay, so let's go back here. Again, thresholding, we have a lower and upper bound, and these are manually defined. That's what these track bars are. These I previously set up. Ignore those two lines. Then we do our warping, which is transforming that full image into an image which only shows the road. We commonly refer to this as the bird's eye view, so a top-down view. This is just for visualization of where the warping happens. And then now we're going to talk about the histogram calculations. Oops, that's Discord. Yeah, okay. This is where the actual code is for the warping, yet perspective transformation. And the cool thing about perspective transformation is that it's inversible. Meaning if you have your matrix already with how to generate a perspective transformation, you can apply the inverse of that matrix to reshape your bird's eye view image back to the original shape. Obviously, you'll lose the pixels that you took away, but the original road will be the same shape. And that's important for like when you want to show end users what is happening. And then the last step is our histograms. So these are the steps we take in calculating of the histograms. We take each of the columns in the picture. So like the leftmost column, then the 0+1 column, 0+2 column, and we sum everything across all the rows. So now we have a condensed picture. So if you think it's 250 pixels high and 500 pixels wide, you'll have an array of size 500, which contains a value. And then we want to loop through the entire array and determine what is the maximum value in there. So what's the greatest pixel intensity in one specific column? And then we'll take that value and we'll multiply it by some ratio that we decide. In our case, in our code, we decide two different ratios, 90% and 10%. And what we're basically saying is we want to only look at pixels that exceed this certain threshold. So if the maximum value is 100 and we say 90%, then we only want to consider pixels that are greater than 90.
Okay.
So we only look at the columns that are greater than 90. And then we look at those columns and we say, okay, what is the average index? And the goal here is to look at which direction are most of these indexing columns, which side are most of these columns on, the left-hand side or the right-hand side of the image.
Mm-hmm.
So we can kind of see that here. Ignore the if statement right now. Well, I guess you do have to look at the if statement. We take the sum of all the columns. That's what axis 0 means.
Mm-hmm.
Then we find the max value inside of that array, multiply it by some ratio, and we look for all the indexes where the value in the array is greater than this minimum threshold.
Mm-hmm.
And then we compute the average index to see which direction is the lane curving most towards. So visually, that's what this looks like. You can see clearly that if we were to take the sum of the left-hand side, there would be a lot more 255s compared to the right-hand side. Like over here, this would definitely be 0. So even if I set my minimum threshold to 1, the range of pixels or range of indexes will be from 0, or I guess, yeah, you can call that 0 to, I don't know, 10.
Mm-hmm.
But most of the indexes lie on the left-hand side. So when we calculate the average, the average value will lie somewhere here.
Mm.
And that's how we know which direction we're facing. But there's one problem with this. We don't really consider where is the center of the lane at the moment we stand. We assume with this strategy that the lane is always starting at the middle of the image.
Mm.
But that might not be the case. The lane might be all the way on the right-hand side and curve really far to the left. Or it might already be in the left-hand side and it's just curving a little bit to the left.
Mm-hmm.
So we want to do another calculation with a histogram only on a bottom portion of the image to look at where does the center of the lane lie where we are currently. So that's what this, okay, that's kind of tiny. Oopsies. That's what this section's trying to show.
Mm-hmm.
It's trying to show that we can define a specific region or a specific amount of pixels that we want to read and do some calculations on. Region equals 1 represents 100% of the vertical image. If we set region to 0.4, then we're considering only 40% of the vertical pixels, starting from
So
the
you
bottom
mean
up.
1 is for 10?
Yeah, the Y.
Okay.
The Y. And then that's what this image dot shape 0 divided by region means. We're taking only a specific amount of rows.
Mm-hmm.
And so how do we use these two calculations, right? We're going to get a curvature value for the bottom half of the image, and we're going to get a curvature value for the entire image. Well, we just subtract the two. We'll take the full image calculation, and we'll subtract it by the current angle from the center point. And this should give us a perceived angle, or like a better calculation on what should our steering be.
Mm-hmm.
Okay. But this isn't always accurate because in our videos we can see the algorithm doesn't always produce the proper lane. And because of that, when you run it through this computer vision steering calculation, we introduce lots of noise, meaning the steering angle might suddenly go right when it's supposed to keep going left. And so we try to reduce that noise with a couple of strategies. We take those steering angle calculations that we have, and we take the average of the 5 latest pieces of data. And we should be giving a weighted average, but it's just an equal average right now. And what we're trying to do is reduce the amount of power that one specific steering angle calculation has. So if it suddenly wants to go right when it's been constantly going left, it will have an impact. But
Mm-hmm.
since majority of the previous entries were always left, it won't affect it as much.
Okay.
Another strategy that you could consider is the extended Kalman filter, and its goal is to try to slowly warp the trajectory um, of what the intended path was. So this black line represents what a computer could possibly want the car to move in. But let's say our starting position was over here at 020, then rather than steeply moving it over to that position, it gradually translates it over. That's the extended Kalman filter. And then additionally, as you've already been trying to implement the PID controller, instead of creating a steering angle which could immediately correct our errors in driving, we decide to slowly change the value, but keep in mind that we do need to reach a specific end goal. So that reduces the chance of the bus steering left and suddenly needing to steer right. And that's pretty much it. So that these two, I guess the main difference is this one is you have an angle, slowly approach that angle, whereas this one is slowly approach the angle with the intention of ensuring you don't need to change directions. This one you might need to change directions still.
Okay, so you mean PID is more accurate for.
The idea is both of them have their downsides. A Kalman filter, usually you have like some variable, but most of it is done automatically, but it's less aggressive. A PID controller, you need to manually set up the arguments for the P, the I, and the D,
Yeah.
and that takes time to calibrate, and it's dependent per machine. And because of that, it's harder to set up, but it's also more aggressive, and it might be more accurate.
Okay.
The downside is if you have the numbers wrong, it will also be very inaccurate.
Okay. Nice.
So in code now, we look at that. Threshold. Okay. Oh yeah, let's go threshold first. In range, it's just looking at a lower bound and an upper bound, ensuring that everything in the image is in between those. Otherwise, it sets their pixel values to black. Okay. Warping, we have a specific width and height of an original image and a set of points describing where we want the new image to lie. So in this case, these 4 points, this trapezoid, and we try to calculate what is that perspective transformation to go from one specific image to another image. And then we apply that matrix, that transformation matrix onto the image. Histogram, we have that percentage, which represents, once we find the max value, how much, what's the bound, what's the threshold to actually consider data. Ignore true, that's just for debugging. And region, representing the second part of the histogram. How much of the bottom half of the image should I be considering to determine the center of my lane? For the full image, just take the entire image. For the portional part of the image, the bottom half of the image, consider only that specific region that we want to look at. Then find the max value in the histogram, find that minimum threshold that we want to only consider, find all the indexes that meet that minimum threshold, and then find the average index of those that satisfy that condition. And then right here, base point is the actual angle. The image histogram is just the image with the yellow ball on it. And that's it. The average is happening right here. And we ensure that the last 5 entries are kept inside of a queue, which is curve list. And we remove entries once it reaches that maximum amount, removing the oldest first.
Okay.
Yes, that explains it all.
Okay. Wow,
Yeah,
there's
that
a
part you
lot
don't.
of to mention.
Like I said, you probably, I don't know if they'll need you to go this in depth. You could just,
Maybe I'll only go through the theory, not the code.
you could like literally just cover that these three processes are happening, and then for histogram, yeah, probably just covering even like a simplified version of this would make sense.
Okay.
Like you can describe how you're taking the sum of all the columns and finding the average index uh, that represents where majority of the data is. That's another way of thinking it. It's like this. If I have an image, a straight lane should look like this. A left turn lane should look something like this in a histogram, versus yeah, versus a right turn lane will look something like this. So that's all the histogram is trying to calculate.
Okay.
That's a simplified way of explaining this.
Okay.
Yeah, the thresholding's pretty easy. These two slides explain it pretty well,
Okay.
or the images explain it pretty well. Warping. This image explains it pretty well, what we're trying to do. Yeah, I don't really have a good image for histogram though.
Okay. Thank you. Let me write
No
about it.
problem.
So
Sure.
you say I must include a histogram and thresholding and wrapping.
Yeah, if you want to discuss this approach to the solutions, then yeah, that's what's happening behind the scenes.
Okay.
Fong's algorithm, I'm not 100% sure how it works. Obviously, I have that PDF, but I don't know how they came upon those layers for the CNN.
Okay. Okay. Thank you.
Yeah, no problem.
Okay.
All
So,
right.
you will come on Monday?
Yeah,
No.
Monday is,
Sure.
yeah, I'll come Monday.
Okay. Okay. Then see you on Monday. Then I will keep doing my slide.
Cool. Okay, we'll look it over again Monday.
Okay. See you.
Bye bye.
Bye.